on to parallel RL circuits. I'm going to skip the inductive reactance part of it. Y'all got that, right? What's the formula?
Two times pi times F times L over area circular mills.
2 pi FL.
No, yeah, F, yeah. I'm not ready to fucking say.
Alright, so first we will get our total resistance. Alright, so we have a total resistance of 66.67 ohms. Then we'll do the same thing with our inductive reactance. I guess I should have told y'all this. In parallel circuits, inductors combine just like resistors do. They're the product over the sum. If there's two of them, the reciprocal method. Same rules that you use combining resistors in parallel. Do the same thing with inductors.
Okay.
So we have a total inductive reactance of 26.914 ohms. Alright, so next we'll calculate our currents going through each component. So the current through our first resistor, we have voltage divided by the resistance. Give us 1.2 amps. All right, same thing on our second resistor. That'll give us 0.6 amps. Our first inductor has a current of 3.822. And our second conductor has a current of 0.637 amps. Alright, so to calculate our total current, we'll add our, up here on our horizontal leg of the triangle, add our two resistive currents together to give us 1.8 amps. On our vertical leg, add them together to give us 4.459 amps. And then we just add those two vectorally to get our total current. That will give us a total current of 4.809. Alright, so now that we've got our total current, we can use that and our applied voltage to get our impedance. So they give us an impedance of 24.95 ohms. Okay, that's the easy way to do the impedance. I'm going to show you the not so easy way. Well, there's sometimes where you might have. Sometimes you might have to use this formula for the impedance, depending on what's given in the problem. All it is product over the sum, the square root. Both of these formulas is going to give you the same exact answer. Again, it depends on what's given in the problem, and whether or not you want to go through all this shit to get where you can put this in. See what I'm saying? Y'all done on this side of the board?
Yeah.
Alright, so now we've got our total current and our voltage, our impedance. Now we can start calculating our powers. So in a parallel circuit, each branch of this parallel circuit is treated as a separate load. Alright, so when we start calculating, we'll have to do each branch. So for the first branch, it's going to be our voltage times the current through that resistor.
I found this on the web.
She is. She's a helpful bitch. Alright, so our power through our first resistor, 144 watts. Alright, our second resistor,
Bless
will be 72 watts. Alright, so our first inductor will be reactive power. Alright, so power at our first inductor is 458.64 bars. And our second inductor power is 76.44 bars. Y'all throw on this side now? Alright, so for our horizontal leg, we'll combine our two true powers. And we'll get 216 watts. And for our vertical leg, we'll combine our reactive powers. And that will give us 535.08 bars. Any guess how we find our apparent power?
Pythagorean theorem.
That's exactly right, Alan. Is there another way to find our apparent power? Huh?
One that you gave me,
You can use a formula, the Ohm's law.
Mm-hmm.
I figured you could.
So this is measured in watts. This is bars. What's this one measured in?
Volt amp.
Yeah.
Oh yeah, that one. Yeah.
It's like V times A, right? So you can just do volts times amps. So we have an apparent power of 577.03 volt amps. Our phase angle. So we have a phase angle of 68.02 degrees. Our power factor is the cosine of angle theta. And that will give us power factor of 37.43%. So at the end of the day, all that our true power is our apparent power times our power factor. Now, if you say we have a poor power factor, it brings down our total usable power down pretty significantly. You remember in our the series circuit, we had a 90.5% power factor. And our the apparent power in that one was 162.84, and our actual power consumed by the circuit was 147.32. So there's not a lot of waste in that one. Y'all have any questions?
Would that also apply to the P reactive or?
No. No, your reactive power, this is power that is stored, but is never consumed. That's why when you have a big number of VARs compared to your true power, you're going to have a tall triangle, right? If you have a tall triangle, it's not a good power factor. Because you've got a lot of waste right there. Y'all have any more questions? Y'all good?
A lot of shit.
It is. It is. For homework for next week, I've got 2 and 3 in AC Theory Level 1. 2 is going to be inductors in series and parallel, what we went over tonight. 3 is all inductive reactance shit. I mean, y'all should be good with that. 2 pi fail a whole bunch of times. Neither one of them's got a whole lot of problems. I think both of them rock under 20 questions. Some of them's got like 4 or 5 parts to a question, but not all of them. Not all of them. 2 and 3, y'all have a good weekend, and see y'all next time.